So now that we know how to create very simple one-layer deep learning protocols, let's talk about how to stack all of these dense layers together to get more complex data transformations. So in this case, you have three layers in between, the last layer being the output layer, and there are two layers here which are hidden because we don't see their outputs. Their outputs are being used in the deep learning algorithm, but ultimately we never know, from our perspectives, we never know the value of those outputs, and that's totally fine because they are going to be used for the succeeding layer to produce the final output. So here we can see the hidden layers all use value activation functions, while the final output layer uses a linear unit. And this is common except in tasks like classification, which might require an activation function on the output, like softmax. So finally, how do we build these layers of neurons inside our deep learning algorithm? We can use the Keras sequential function, inputting a list of layers that we want to input. So in this case, we have three layers inside the model, the last layer being the output layer, and two hidden layers in between, each using the ReLU activation function. So here we can see the input shape is 2, meaning there are two inputs into the first layer, which itself has 4 units of neurons, leading up to the second layer, which has 3 neurons, all leading to the final output layer, which only has 1 neuron. So we are passing in all of these layers together in a list instead of separate arguments. And as usual, to add an activation function, just make sure to use the activation argument. So this is more close to what you see a typical deep learning algorithm will have. You have a number of layers, each with hundreds and hundreds of neurons. So in this case, we have 3 hidden layers, each with 512 neurons each, and all of them leading to one output layer, which only has one neuron, which uses the linear activation function. Okay, and now that's done, we can talk about how can we compute the accuracy of our deep learning algorithm. So we can find out how close it is to the expected output by using what we call the loss function. So the loss function effectively computes how far away your actual output versus the expected output. It measures the disparity between the true value and the value that the model predicts. So the what you count as the target's true value depends obviously on the input. So say for example, if you are tasting wine, the output will be the red wine quality, or it might be the price of a house or the fuel efficiency of a car. It all depends on what you're trying to find. But point is, there are multiple ways that you can compute this, the easiest of which is using the mean absolute error, or MAE, which really is just computing the actual absolute difference between the true output and the predicted output. So in a graph, you can see this straight line as the predicted output and these dots as representing the true values that we expect in the output. So for example, given an input of 0, we see the predicted output is 0, but the actual output is like 1.2 or something. So the loss will be, in this case, around 1.2, and then you add up all of these together, and then you average all of them together, and then you get a mean absolute error value of 0.993. So in other words, it is the average length between the fitted curve and the actual output data points. And obviously, besides MAE, you have other loss functions such as the mean squared error or the Huber loss function, both available in Keras.